Today we will be discussing the derivative or the slope of equations that have an exponent higher than 1, or usually they are curves. First, I would like to show the difference in writing y. So instead of using y, for example, the slope intercept form y is equal to mx plus b, we will now change the variable y into the function of x. So mx plus b. So this is needed because in subsequent discussions there will be composite functions wherein y will not be longer be appropriate. So for example, we have a line. We have 2 points in the line. So the slope of this line is denoted by y2 minus y1 over x2 minus x1. Now, because we are changing the variable y into function of x, so for example, we have 2 points again. So if this is x1, x sub 1, so your y, we don't use the y anymore. We will use the function of x sub 1. So this is your y. And then if this is the second point, x sub 2, so this is now the function of x sub 2. So your new slope would then be, if we put x1 y1 x2 y2, so your slope, if we have a new protocol for writing, would now be y2. So f of x sub 2, that's your y2, minus your y1. Your y1 is f of x sub 1 over your x is the same, so x2 minus x1. I know it's a bit confusing. Instead of using y, we will be using the function of x. Now, let us consider an equation y is equal to x squared. So now we will again rewrite this one. We no longer use y. We will use f of x is equal to x squared. So this is not a straight line, but this is a curve. It has a power higher than 1. It is actually called a parabola. This is the shape of the curve. So to plot some points, so we just plug in a value on x. So for example, you want to find if x is 0, so this is how you write it, the function of x at 0. So you replace x with 0, so that's still 0. So your f of x, that's your old y, is 0. And then if you want to find the value at x equal to 2, so 2 squared, that is 4. So that will be here 2 and 4. And then you can plot. So I have plot more points. So this is your 0, 0. This is your 1, 1. This is your 2, 4. This is your 3, 9. This is your 4, 16. And this is your 5, 25. This point. Okay. Now, for example, we want to know the slope at this point. Now, the slope at that point is the is the line tangent to the curve that is tangent to this point. So this is the slope that you want. Now, so we cannot use only one point to get the slope. We always need 2 points. For example, here we need 2 points. We can try to approximate by drawing, for example, a second line. A second line is a line within the curve, and if you connect it, it's called a second line. So we can get the slope of this line. So from point 520 to 24. Now, to get the slope of these 2 points, which is the second line in the curve, we just use the slope formula. So the slope would be, so it's still y2 minus y1, so 25 minus 4, 25 minus 4 over 5 minus 2, 5 minus 2, that would be 21 over 3 or 7. So the slope of this second line is 7. Now we can try to this slope is slightly different from this one. This is the one that we want. We can try to make it closer by using this point and the same point. So that would be this line. So the slope at that point would now be 16 minus 4 over 4 minus 2. 4 minus 2. So that would be 12 over 2 or 6. So the slope of this line is 6 or 6 over 1. The rise over the run is 6. But this one is still different from this one. It's still higher. So we want to try this point. So to get that point, we get the slope from here to here. That would be 9 minus 4 over 3 minus 2. So that would be 5 over 1. So this one, although closer to the line that we want, so this is the slope at this point. So this is still a bit different from this one. Now we can add. So what I want to show is that the closer I get to this point, the closer is the slope also to get to that exact point. Now the closer I get to 2, the better will my slope would be closer to the actual slope that we need. So let's say, so your x is 2. Let's say I will put a point close to 2, but not 2, because we cannot use the same point. It will become 0. So let's say 2.1. If we use 2.1 as your x, the function of x at that point would be 4.41. So your slope at that point would be so that point will be here, very close. That would be 4.41 minus 4 over 2.1 minus 2. That would be 0.41 over 0.1. That's 4.1. So it will be close. Now if you notice, it gets closer and closer to 4. Now we'll put another one closer, much closer to 2 than 2.1. So let's say 2.01. This one is closer to 2 than 2.1. So if you square this one, the function of x would be, I'll just put it in here, 4.0401. So the slope at that point would be 4.0401 minus 4 over 2.01 minus 2. So that will be 0.0401, sorry, 0.0401 over 0.01 or 4.01. So the closer we get to 2, the closer the 2 points together, the slope gets closer and closer to 4. And actually the slope of the curve at that point is actually 4. We can now make a general formula for the slope of a curve. So first, I would like to maximize this point, the one where we want to get the slope, and we will put general numbers or general variables so we can use it at any point. So I will magnify this one, so it will become like this. Now this is your curve. For example, you have a point in here and another point in here. So let's say this one, this distance is really small. Because I magnify this one, this is actually infinitesimally small. Now, if this is your x, if this is if the distance from here to here is x, so this is x, and then the y component would be f of x. So the distance from here, let's say, so this is x. That's why the point in here is x. Let's say if the distance from here to here, let's say this is h. The distance from here to here is h. So this point would have the value x plus h, because this is x. Now if this is h, so this point is x plus h. Now the y component would be the function of x plus h. So we can now get the slope of this curve. So that would be, to make it easier, let's put a notation x1 y1. So your slope is y2 minus y1. Just move it here. So your notation is y2 minus y1. So we will write this one, f of x plus h, which is your y2, minus y1, which is f of x minus f of x, over x2. Your x2 is actually x plus h. X plus h. Oh wait. This is x plus h. x2 minus x1, but this one is just x, so my x2 minus x1. Now in here you have an x and then you have a minus x, so you can now cancel out this one. So what you have left in your slope will be f, the function of x plus h, minus the function of x over h. What is left in here is h. So this equation is called the difference quotient. Difference quotient. This is the slope of the curve, or this is also called the derivative. Another term is the function f prime of x. So you can either use this one or this one or this one. Let's just use this one as a shortcut. So you can now find the slope of any curve using the difference quotient. So using the same curve, so our curve is I will repeat it here. Y is equal to x squared. Y is changed to f of x is equal to x squared. We can now use this equation to find the slope of that curve. Okay. So we call it the f prime of x. That is the derivative. So we follow this one, f of x plus h. So the function of x plus h, we will replace x plus h into x. So the function of x plus h will be x plus h squared. So what we did is, whatever is the x in there, we change it into x plus h. There is a squared, so we put the squared. So that will be the function of x plus h minus the function of x. The function of x is this one. Function of x is x squared. So we'll put this here, x squared minus h. Now, this is a binomial. If it is squared, the answer would be x squared plus 2hx plus h squared. That's the square of the binomial minus x squared all over h. So that will be your f prime of x, f prime of x. But this one is x squared and minus x squared. This can cancel out. So what you have left is 2hx plus h squared all over h. Now, this one and this one, they both have an h. So we can factor out the h. What you have left is 2x plus h over h. Now we can cancel out h and h. So what you have left is 2x plus h. So this is your f prime of x. Now, as you recall in here, the distance between these 2 points, this h is so small, this is so small that we can actually put it to 0. So this is really, really small that we can put it as 0. So this h becomes 0. So the slope of the curve is 2x. So this is the slope of the curve, of this curve. Now what does 2x mean? Every point in the curve has a different slope. For example, you want to find the slope at 2, 4. So this is your point 2, 4. This is your x, this is your y. So your x in here is 2. You will plug in this value into your x to find the slope at exactly this point. So that would be 2 times 2 is 4, or 4 over 1. So at exactly this point, this line has a slope of 4 over 1. Now you can find the slope at other points. For example, if you want to find the slope at 416, so here your x is 4. So you plug in the value of 4 into your x. So you want to find the slope at this point. So your 2x, you change x into 4. 2 times 4, 8, or 8 over 1. Your rise over run is 8. So at exactly this point, if we will draw a line, this is your slope. At this point, this line has a slope of 8 rise over run. So you can use at any point. You can get the slope at any point in the curve using the derivative, using the difference quotient formula. Now going back to the original equation, the original equation is f of x is equal to x squared. Now using the difference quotient, we were able to get the slope of the curve as 2x. Now let us compare what happened from the original equation to the derivation method. What we will notice is that the exponent went down to the front, and that the exponent, this is x to the first now, the exponent was reduced by 1. Now we can make a general rule on how to derive the equation without using the difference quotient by using a shortcut. So in general, using this analogy, if you have the function of x to the n, the derivative of that one will be, this one goes down to the front, so n times x to the n minus 1. So this is called the power rule. This is a shortcut of the difference quotient, so we don't need to do the long method of difference quotient. We can use the power rule to do a shortcut on doing the derivation. Now let's take an example. So example, your equation is very complicated. 5 to the 5x cubed minus 2x squared plus 3x plus 4. Using the power rule, so this one goes down into the front, so it will multiply to 5. So this is your f prime of x, your derivation already. This becomes 15x squared. You subtracted 1 from 3, it became 2. Now 2 will go into the front, multiplied to 2, it will become 4x. So 2 minus 1 is 1, so 2x to the 1. Now in 3, so this is 3 to the 1. So this one goes into the front. 1 times 3 is still 3. But if you subtract 1 from x to the 1, this will become x to the 0. X, any number or variable raised to the 0 power is equal to 1. So your 3x became 3. Now what about 4? Actually, 4 has an x to the 0 power. So, but it was not, because the x to the 0 power is 1, so we don't write it anymore. But if you do the derivative, so 0 goes to the front, 0 times 4, actually the x will become x to the negative 1, but since 0 times 4 times x to the negative 1 is still 0, so we don't need to write it anymore, the 4 disappears. So this is your slope for the curve. And then whenever you have the x, you substitute the x in here, and in here you will get the actual slope of the curve. Now, equations that has a higher degree, a degree meaning the highest exponent of the equation, of degree 2 or 3 or 4, it will have different shapes of curves. So, for example, the parabola, it would shape this like this. Sometimes for cube equations, equation that has the exponent of 3, where the variable has an exponent of 3, it will look like this, or it would look like that. Sometimes like this. Now, these curves have they call it a relative minimum or relative maximum. So these points, the lowest points and the highest points relative to the curve, these are called the minima. This is called the minima, and this is called the maxima. This is the minima. So whatever the lower point is called the minima. This is the maxima, these two. Because it's called relative maxima, relative maximum, because this would go on forever, so your actual maximum is infinite. So, but this is a relative maximum. This is a minimum. Absolute minimum is infinite. In here, this is called the relative maximum. This is called the relative minimum or minima. Of course, it will extend infinitely. Minimum will extend infinitely. The maximum will extend infinitely. But these are called the minima or maxima. Finding the minima and the maxima is another important application of the derivative, because this can be applied not only in math, it can also be applied in physics, business, economics, and many other fields. So our next topic will be to find the minima and maxima. By the way, for example, you have a curve like this, and you want to find the minima and the maxima. The slope at exactly the minimum and the maximum is exactly 0, because the slope at this point is exactly horizontal. In here, the slope is also exactly horizontal. Of course, in here this is negative, this is positive. But at this minima and maxima, the slope is 0. Slope is 0. So your slope is the rise over the run. But in here, there's no rise, only run. So this rise will be 0 over the run. So your slope is 0 at this point and at this point. Let us consider an equation. The function of x is equal to x cubed minus 12x plus 1. Now, this is degree 3, because the highest exponent of the variable is 3. So it is a higher degree 3 equation. Now, using the power rule, we can now easily get the slope of this curve, or the f prime of x, or the derivative. So using the power rule, this one goes down in the front. It becomes 3x. This one minus 1 is squared. And then here, this has an exponent of 1. This one goes in the front. 1 times 12 is still 12. But because this one minus 1 is equal to 0, so x to the 0 power is 1. Now, this was only now 12. And I have explained earlier, this one is a power of x to the 0 power, so use 0 multiplied to 1 becomes 0, so 1 has disappeared. So this is now your slope for the curve. Now you want to get a slope of 0. So to get a slope of 0, you want this one to be equal to 0 to get at what point is x will have a slope of 0. So we equate it with 0, so this slope will make it 0. So whatever x we can find, that x will have a slope of 0. So 3x squared minus 12. Now we can factor out 3. So factoring out 3, you have x squared minus 4 is equal to 0. We can divide both sides by 3. So 3 will cancel out. Now x squared minus 4 is a difference of two squares. So we can again factor it out. X plus 2, x minus 2. Now we equate this one to 0, we equate this one to 0. X plus 2 is equal to 0. X is equal to negative 2. This is one of the values that is either minima or maxima. And then this one we equate to 0. X minus 2 equal to 0. X is equal to 2. So this is also these two are critical points that is either a maxima or minima. Now let us plug in some points. For example, if x is 0, so the function of x, we just plug in the value of x in here to get the value of the function of x. So for example, so if f of x is, if f of x is 0, then we substitute all 0 into all the x's. So 0 to the third minus 12 times 0 plus 1. So your f of 0 function, f of x at 0 is 1. So your f of x is 1. And then again we can we just plug in any value of x, and then you put it in here. If f of x is 2 cubed minus 12 times 2 plus 1, that would be negative 15. So I just plug in all the values. Negative 2 is 17, 4 is 17, negative 4 is negative 15, 6 and 145, negative 6 is negative 143. So if we plug it in this, if we plug these values into the graph, so 0, so let's say this is 1, 2, 3, 4, and 5. I made this into I've shortened the y-axis. This is 5, 10, 15, 20, 25, 30. This is 5, 10, 15, 20. Now 0 and 1, so 0 and 1 would be here approximately. 2 and negative 15, so 2, 1, 2, negative 15, oh this is negative, so 5, 10, 15, so 2 and negative 15 is around here. Negative 2 and 17, negative 2, this is negative 2, so this is 15, so this is around here. So 4 and 17, so 1, 2, 3, 4, and then 17, so it's less than 20, it's around here. negative 4 and negative 15, so 1, negative 1, negative 2, negative 3, negative 4, and negative 15 will be around here. Oh wait, negative 15, negative 4, negative 15, it will be around here. So 6 and 145, so 1, 2, 3, 4, 5, 6, so it's around here. It will be way up here. And then negative 6, negative 143, so 1, 2, 3, 4, 5, 6, and then way up here. Now we can now draw the line. See, it will be looking like this. Now, as we have seen, x is negative 2 is this one. So this is a maxima. This is maxima. And x is equal to 2. This is the lowest point. Sorry for the drawing. This is positive 2. This is minima. This is minima. So that's how you find the maxima and minima in a curve. For more explanation, for more comprehensible explanation, you can watch Calculus 2, Calculus 3, and Calculus 4 of my previous video. It will be explained more fully. This is just a summary of those 3 videos.